my name is Dan Oak, and I'm a student at Athabasca University, currently taking the course Computer Science 444, Embedded/Robotic Programming. And if you've been following the videos I've been posting on the course forum so far, you'll know that I'm going through the SparkFun Inventor's Kit Guide, and I'm showing you the way that I've done a couple of the projects. In a previous video series, I've done Project 1 and its associated circuits, and in a separate video series, Project 2 and its associated circuits. And today we're going to be going through Project 3, specifically Circuit 3A, the first circuit associated with Project 3. So, in this video for Project 3 of the SparkFun Inventor's Guide, we're going to explore Circuit 3A, which introduces the use of servo motors. A servo motor is a type of motor that provides precise control of angular position, making it an essential for applications in robotics and automation, which is the whole reason we're taking COM 444, to learn about robotics. In this circuit, we'll use a servo motor, a potentiometer, and some jumper wires, as well as a breadboard and the microcontroller. The potentiometer allows us to control the position of the servo by adjusting its angle based on the input we provide. We'll connect these components on the breadboard and then dive into the Arduino code. The first thing to note is the inclusion of the servo library when we get to the code, which enables us to control servo motors with ease. So we could actually control the servo motors just using pulse width modulation, coding ourselves to control the servo motors, but it would be a lot more cumbersome and just a lot more code behind it. And again, the whole point of programming is not to reinvent the wheel, but it's to stand on the shoulder of the giants that have come before us. Reuse other code that people have made and just use it in our particular programs, and that's the whole point of coding libraries. So the servo library is one such library where there's a lot of code in there that allows us to get working with servos fairly quickly. So one particular command, the command myservo.attach servo pin, which you'll see in my code shortly, links our servo object to a specific pin, digital pin 9. It's essentially the pin mode function, but for servos. In the code structure, we have the setup function, which initializes our settings and runs once, as setup function does, and the loop function, which continuously reads the input from the potentiometer. We'll use the map function to convert analog values from the potentiometer, which range from 0 to 1023, so that's the analog values that you can read on one of the analog pins, and we're going to map that to the corresponding servo positions that we wish to move our servo between, so from 20 to 160 degrees. Now servos actually typically range from 0 to 180, but when you go to the extreme, sometimes the servos get jittery and shaky, much like the robot that we may have read about in the course textbook. So we're going to keep away from those limits and just limit ourselves to angles of 20 to 160. I have also created a coding challenge that implements 3 modes. Reverse mode, which moves the servo opposite to the potentiometer. Rescale, which limits the servo movement to a smaller range of 80 to 110 degrees. And light, which controls the servo based on inputs from a photoresistor. We'll discuss how to switch modes using the serial monitor, and I'll explain the importance of trimming commands, i.e. the trim command, to make sure that we have accurate input when we receive text or input from a user. Additionally, we'll look at how Boolean flags help manage state changes without unnecessary repetition in the output. I essentially added Boolean flags so I don't just repeat output every loop. And we're going to go through the code, and then I encourage you guys to experiment at home and do your own coding challenges and actually type in some code and play with the circuits. The best way to learn. So without further ado, I'll show you the circuit that I've created. So it's a very simple circuit right now, and there's the servo. I've got a potentiometer, and this is a voltage divider using a 10 kilo ohm resistor and a photoresistor, and as well as the breadboard microcontroller. And we'll get right to the code. So first thing we're going to do is going to jump through the guide here. We're going to get right to the spot that we need to. Okay, so in the previous videos we've went through the guide up to this point. So right now we're on page, it looks like to be 56 or so. So 53 in the actual guide, showing up as 55 in the PDF viewer. But anyway, what is Project 3? Well, Project 3. Imagine you're tired of your cat walking all over the kitchen counter, how about the dog getting into the garbage, and you need a way to stop your younger sibling from sneaking into your bedroom. Learn how to protect against all of these annoyances as you build a multi-purpose motion alarm. The alarm detects distance and motion using an ultrasonic distance sensor and creates motion using a servo motor. So that's ultimately what Project 3 is going to do. We're just going to be focused on the servo motor in this video because we're just going to be focused on Circuit 3A. So Circuit 3A, servo motors. In this circuit, we're just going to be talking about servo motors which move to a specific position. Unlike a regular DC motor, which just spins and spins as you connect the leads to a positive and negative voltage, or positive and ground rather, and the DC motor just spins. And if you reverse the leads, it will spin the opposite direction, but it's a full 360-degree spin. Servo motors typically don't do that. They move to a specific position and then they stay there. And they were originally used to steer RC airplanes and cars. But really they can be used in any project where precise movement is needed. So as you can see in the guide, the components we're going to use is a potentiometer, a servo, some jumper wires, and scissors for cutting some adhesive tape. So the servo motors. Servo motors, like I said, are just like regular DC motors in that they have, regular DC motors have two wires, and the motor just spins around and around, like all the way around 360 degrees and again. Servo motors, on the other hand, have three wires. One for power and one for ground, just like a regular DC motor, but there's a third wire which is for the signal. And when you send the right signal through the signal wire, the servo will move to a specific angle and stay there. So the common servos rotate over a range of about 0 to 180 degrees. The signal that is sent is a PWM signal, so a pulse width modulation signal, which we've talked about in our previous videos, and if you've been going through the guide in order up to this point, you would have already learned about that. And basically, there's only a few pins on the microcontrollers, an Arduino compatible microcontroller, that is capable of doing pulse width modulation. That's pins, the digital pins 3, 5, 6, 9, 10, and 11. And as I've demonstrated in previous videos, if you look on the digital pins here, which are these 14 digital pins here, 0 to 13, the pulse width modulation capable pins have a little tilde symbol beside them. So you can see beside 3, 5, 6, and then 9, 10, 11, there's the little, looks like just a dash at this zoom in level, but really that's a little tilde symbol. The same symbol you'll find on the key to the left of your 1 on a keyboard. But that little symbol just indicates that these digital pins are capable of pulse width modulation. And what is pulse width modulation? Well, as explained in previous videos, most digital pins you can just send either a high or low signal to, either 5 volts or 0 volts, meaning you can turn something on or off. So there's two states for most digital signals. With a pulse width modulation signal through those particular pins, you can actually send any value between 0 and 5 volts. And it has a resolution of, you can send anything from 0 to 255. So there's 256 different levels that you can send. This is just talking about how to attach your servo using some two-sided adhesive strip. So, as we said with pulse width modulation, this also says that including your servo motor are a bunch of these connections that you can attach to your servo, which definitely will allow you to be able to see the position and use depending what you're using your servos for. Perhaps a helicopter using this, or just some wheel, or anything. Some of the new concepts we're going to talk about today are the duty cycle. So the pulse width modulation, PWM, is a great way to generate servo controls. So the length of time that a PWM signal is on is referred to as its duty cycle. So the duty cycle is measured in percentage. So for example, if the PWM signal is high for half of the time, it has a 50% duty cycle. It means it's on for 50% of the time. if it's high for 3/4 of the time, it has a 70% duty cycle. Because again, we're measuring the duty cycle in percentage. And if it's only high for 1/4 of the time, it has a 25% duty cycle. If it was high 100% of the time, it would still be a pulse width modulation signal if you're using PWM pins and you're programming accordingly. But it would be the same as just using a digital right at that point, turning something on. High, 5 volts. Just like if you had a 0% duty cycle, it'd be akin to a low signal if you use digital right. So anyway, as it says here, a duty cycle of 50% means the signal's on 50% of the time. So the variation in the duty cycle basically tells the servo which position to go to. And then we're also going to learn more about Arduino libraries. So the Arduino IDE has hundreds of built-in user-submitted containers of code called libraries that are already included as soon as you download the Arduino IDE from the Arduino website. And then there's certain other libraries that you have to install. The good news is you can install most of these libraries fairly simply. You can either go to an external website, just Google the library, and a lot of times you're going to find them on websites like GitHub and you can download them. Or you can often just go to click this, depending what Arduino IDE you're using, this little icon of books here, and this is your library manager, and you can just type in a library that you want. In this case, if I wanted the Servo library, I type in Servo, and I could just click install and download the Servo library there. But there's lots of different Servo libraries here, and I already have the capability in there, so I don't actually need to download it. But libraries, again, as I said, is someone else has already done a lot of the hard work, a lot of the coding for you, and just made a user-friendly library that just has a lot of functions you can use right out of the box, so to speak. So that's what we're going to do today with the Servo library. And it just, again, allows us to control a servo with just a few lines of code. Now, to use one of the built-in Arduino libraries, we have to use the include statement. So you go #include or #include, depending what generation you're from, and then the header file. This is enabling your code to use all of the library functions associated with that library. So the Servo library, in order to use that library, you just add the following line of code: #include, and with angle brackets, servo.h. And sometimes you'll see angle brackets, sometimes you'll see double quotes. Angle brackets are typically if it's kind of a built-in library, one associated with the actual language, so to speak. And double quotes are more of a user-defined header file, something that you might create yourself or that's not really recognized as built-in case. Anyone who's familiar with C and C++ programming, which is what Arduino programming is based off of, again, knows the difference between the angle brackets and the double quotes is built-in versus user-defined. We're also going to be talking about objects and methods, which anyone who's familiar with object-oriented programming knows about that. And the reason being is because the library, in order to use it, we're essentially going to create an instance of the Servo library, so an object of type Servo. And then we're going to be able to use the methods, methods are just functions associated with an object that you instantiate from a class. So we're going to be able to use the methods or functions to easily interact with the servo. So we're going to create a myServo object that's just an instance of the servo, and then the main method that we're going to use is write method. And the write method allows us to tell the servo what angle to go to. And again, typically from 0 to 180 degrees. And why would we want to go through the trouble of making an object and a method instead of just sending a servo control signal directly over a pin, as I said earlier? Because we could do that. It would just be a lot harder, so that's why. This is the basics of a servo motor. Again, there's 3 pins with a ground wire, a 5-volt power wire, and the signal wire. And then you're going to hook it up as such, as shown here in the nice little guide and schematic that SparkFun has provided. Basically, you're just having your potentiometer hooked up as we have done in a lot of projects. One of the external terminals or pins is hooked into the positive rail of the breadboard. The other external pin is hooked into the negative rail of the breadboard, and both the positive and negative rails of the breadboard are connected to 5 volts and ground of your microcontroller respectively. And then the middle pin of the potentiometer, known as the wiper, is connected into one of your analog's inputs. In this case, it's connected to analog input A0. And then your servo motor, the power and ground wire is connected to the power and ground rails of your breadboard. And the signal wire, which is that white wire, is connected, in this case, to digital pin 9. Again, it could be connected to any one of the PWM digital pins. That's pins 3, 5, 6, 9, 10, or 11. We've just happened to chose 9 in this tutorial, but it does have to be a PWM pin, one of those pins with the tilde symbol. So again, that's the schematic, and you'll see that in the my microcontroller breadboard setup, I do have that done up. So I've got my potentiometer. So I've got a ground and power rail on this side of the breadboard as well as this side of the breadboard, and I've got them connected together. So this gray wire goes from ground to ground on both sides of the breadboard, and this red wire goes from the power rail on this side to power rail on this side. So, and then I've got the power and ground rails of the breadboard connected to the 5-volt and ground of the microcontroller. Also, you'll see that I have the potentiometer. You can't see the pins of the potentiometer, but basically this gray wire here that goes to ground is connected to one terminal pin of the potentiometer. The red wire that goes to power is connected to the other terminal, and right in the middle we have this blue wire, which is connected to analog pin A0. And then this setup here is a voltage divider setup. I can just talk about this quickly, but this is for the coding challenge. But basically, I've got a 10 kilo ohm resistor connected to ground, and then the other end is connected, shares a connection with one end of the photoresistor. The other end of the photoresistor is connected to the power rail. And then the common connection of the resistor and the photoresistor, I'm pulling that through the yellow wire into analog pin A3. But that is for the coding challenge. We'll talk about that in a minute. Back to the servo motor. The servo motor connection, again, it has wires white, red, and black for the signal, power, and ground wire. But then I've reconnected them into this 3-wire harness, which the purple wire is now acting as the ground, as you can see. The white wire, gray wire, it's kind of hard to tell in the video, is now the power wire, and the white wire is still the white wire, your signal wire. So again, I've got those hooked into the power and ground rails here, and my white wire connected into digital pin 9, which is that PWM pin as indicated by that little tilde symbol. So let's get right to the code then. Okay, so as usual, SparkFun does their multi-line comment, just indicating what they're doing, so what the code does. So in this case, it moves a servo attached to pin 9 so that its angle matches a potentiometer attached to A0. You can click the links and view the circuit diagram and instructions and download the code. So as you can see right away, we include the servo library so that we can use it. We create a couple instance variables for the pot position, which is the variable to store the position of the potentiometer, and the servo position, which will store where the servo will move to. And again, both those are variables because they're both going to change. The pot position is going to change based on us physically changing it, and the servo position will change accordingly. So then we're going to create an instance of my servo. So my servo, so that's basically, again, it's kind of being declared like a variable for those who are not familiar with object-oriented programming. Instead of saying int or float or bool or something like that, we're just calling the name of the class. In this case, the class is servo, and it's an uppercase S, you'll notice. And then you can give it any name. I called it my servo. That's kind of a common convention, but you could have called it anything for that matter. Servo 1, you could have called it Bob. But anyway, we create an instance of the servo class, so now we can use this instance and call the methods associated with the servo library. In setup, instead of calling the pin mode this time, we're going to go myservo.attach. So you call the attach method and pass in the pin to which you want the servo to be attached to. We know it's attached to digital pin 9 in our case, our PWM pin. So this method is essentially doing what pin mode does. Where normally you call the pin mode function, you pass in two arguments, the first one being the pin that you're attached to, and the second one being whether it's input or output. But in this case, the servo is always going to be an output because we're always sending a PWM pin to the servo motor. It's an actuator, not a sensor. So we're always going to be treating it as an output. So there's no need to call pin mode and do an output. The people who made this library have already done that behind the scenes for us, and so we instead now just call the attach method. You'll notice that in their examples they're just using magic numbers like 9. Again, I think it'd be a little better if you just created a constant or a define function and went servo pin, something like that, and then use that servo pin in your code. But the example, not sure what's happening there, but the example just uses 9 as a magic number, and that's fine. They're simple enough examples. But again, if you're making your own code, sometimes it's a little more explicit to do those defines or make a constant. And then in the loop function, we're just going to do a simple read, analog read on pin A0, and assign that value to pop position. Again, the analog read is going to give us a value between 0 and 1023, and we're going to assign that to our pop position. We're then going to use the map function, and I've talked with the map function before, but just as a quick refresher, it basically takes in 5 arguments. The first argument is the variable, in this case, that's going to store the pop position. So again, we know that that variable is going to have a value between 0 and 1023. So again, the first argument is some integer variable that has an integer value. The next 2 arguments are going to be the minimum and maximum range of that variable. And then the 4th and 5th arguments are going to be a new range that you want to create for that variable. So this will now correspond with the minimum, and this 5th argument will now correspond with the maximum. So we're remapping the potentiometer value, which is normally from 0 to 1023, and we're remapping it to 20 and 160. So when we turn the potentiometer to 0, we're going to effectively make the servo position 20, because that's where this map function is getting assigned. And if we have the potentiometer turned all the way up to 1023, all the way to one end, we're going to assign 160 to our servo position. And then finally, we're going to call the write method, which we see in there in the SICK guide. We're going to call the write method on my servo, which is that object of servo that we created, and we're going to pass in the servo position. So this is going to be a position between 20 and 160, and that's going to move the servo to that position. So without further ado, let's upload this code. So if I go Tools, I'm on port COM11. I've got the board registering as an Uno. I'm going to upload the code, and we'll see what happens. Let me get a screwdriver. So, as you can see, I'll turn it like this. So I'll put the screwdriver in the potentiometer here. So when I've got the screwdriver all the way turned to 1023, the end position, the servo motor is at a position of 160, which makes sense because that's, again, what we're supposed to be mapping to. When we have the potentiometer all the way at 1023, all the way to one end, we'll have an angle of about 160, and when we have it at 0, we'll have an angle of 20. So in this case, I guess counting this would be an angle more of 20 when I have it at one end. It just depends on how I've got the wiring, which one is to ground and which one is to positive. But when I go to the other end, it'll go to the other angle. So whatever you want to call this, if this is 160, let's say, I'm at 1023, and then when I'm at 0, it's at 20. But again, going between the two extremes of the potentiometer takes me between an angle of 20 and 160. And we'll try to leave it right there in the middle-ish. And that's as simple as this code is. Again, it's just your potentiometer being read in at pin A0 and controlling your servo position through the map function. So that was the basic circuit, which we'll just show the code for that. So again, the basic circuit looks like this. Again, what are we doing? We're using a potentiometer to cause the servo arm to turn, and the servo will mimic the movement of the potentiometer. The main program code here, the overview, is that we're going to read the value of the potentiometer, then we're going to convert the potentiometer value, which is between 0 and 1023, to an angle between 20 and 160, and tell the servo to go to that angle. The main things in the code to note are that we're including libraries, so hashtag include command adds a library to the Arduino program, and then you just need to put whatever library it happens to be, in this case the servo library. And then we're creating servo objects. Again, if you're familiar with object-oriented programming, you'll be familiar with creating objects, instances of classes. So again, we use the name of the class, which is uppercase, and then just give it a name. By convention, you often give it a name of my servo, but you could have called that anything. Again, you could have called the servo Bob. And then we're using the attach method. The attach method tells the servo which pin the signal wire is attached to. In our case, it's digital pin 9, and it has to be a PWM pin. So again, only use digital pins capable of pulse width modulation, which have that little tilde symbol on them. And then we use range mapping. So we use the map function to take a range of value outputs and convert it to a different range that could be more or fewer. In this case, we took the range of 0 to 1023 that the potentiometer gave us, just reading in on the analog pin, and we mapped it to a range of 20 to 160, the angle that we wanted our servo motor to go through. And then we use the right method associated with the servo, quite possibly the main method associated with servos, and what you're passing in there is an angle that you want the servo motor to go to, between 0 and 180 typically for most servo motors. But again, using the extremes of 0 and 80, you might get some shaky, jittery effects for the servo motor, so it's often best to not go quite to the limits. In our case, we went from 20 to 160. But again, that right method moves the servo to a specified angle. And then finally, there were some coding challenges. So the coding challenges associated with this circuit were they wanted us to try to reverse the servo direction, so try making the servo move in the opposite direction of the potentiometer. And then they wanted us to change the range, to try altering the map function so that moving the potentiometer a lot only moves the servo a little, or vice versa. And then finally, we're going to swap in a different sensor. We're going to try swapping in a light sensor in for the potentiometer, and then you can make a dial that reads how much light is present. So let's get right to it. So this is the coding challenge right here. This is the code associated with the coding challenge. I'll just get this bigger. I'll try to go through somewhat quick because I do have to take my kids to jiu-jitsu in 15 minutes. But as usual, I've got some Doxygen style comments. This extra asterisk, not asterisk here, this extra exclamation mark here sets this up as a Doxygen style comment. It basically, again, if you've been following my videos, you know that this type of commenting allows your program to be put through an external program such as Doxygen, and that program will generate some really nice professional looking HTML files for you that just are really nice documentation of your code. Oftentimes I'll use a double asterisk here instead of this exclamation mark. Oh, what did I do there? Seems like I'm having some issues with the keyboard, but I'll use a double asterisk. It does the same thing as this. The difference is that sometimes I just try to do the different things just so I can try to remember all the different ways there are to do stuff. But for example, with Doxygen, if you just look up how to do Doxygen commenting, you can either use the double asterisk version or the asterisk exclamation mark. And the main difference is this one is kind of using the JavaDoc style, and this one is using Qt style. And then, for example, you can use 3 forward slashes to inline comments using the JavaDoc style, or / exclamation mark for the Qt style. So there's different styles here, but again, that's not the main focus of this video. So, but I'll quickly try to go through what we're doing. We still add the servo library as usual. I've created constants for all my pins because, again, I like having constants, so I've used the const keyword in front of all my variables, and I've used uppercase letters, uppercase letters with words separated by underscores for my constants. That's a convention, not a syntactical rule. So again, my servo pin is on pin 9, pot pin, my potentiometer pin is on A0, and light pin, my photoresistor, is on pin A3. Again, I could have used hashtag defines for these as well. I just like constants. I've also used constants for my ranges of my servo. So my minimum range is going to be 20, as we've seen before, and 60 for my maximum range. Again, you don't want to go to those extremes of 0 and 180. And then my rescale range, this is one of the coding challenges, if you remember, is to make it so you can move the potentiometer a lot, but only move the servo a little. So I've got a rescale range. The rescale minimum value is not going to be 20, it's going to be 80, and the maximum value is going to be 110. I've created my servo object, so servo, my servo. I've given it the same name. These are my global variables. I've created a string variable called command, and that's something I'm going to use because I'm going to be actually typing in commands into the serial monitor in order to dynamically change which coding challenge we're working with. And this int variable current mode, which I've got set to 0 by default, tracks the active mode. 0 if I'm in the default mode, which is just like the last circuit. 1 if I'm doing the reverse mode, which is the first code challenge. 2 if I'm in the rescale mode, the second code challenge. And 3 if I'm in the third coding challenge, which was to use a photoresistor to control the servo position. This variable here, Boolean mode change equals true. This is a Boolean flag I'm using to control what I print on the screen. So basically, I want to be able to print to the serial monitor what mode I'm in, if I'm in default mode or light mode or reverse mode. But I only want to do it once. I didn't want to do it. I just didn't want the screen just to constantly be like saying default mode, default mode ridiculously. So this is just to basically control how my output looks in the serial monitor. Again, these are all Doxygen style comments. I've talked about this before. If you're interested, go look on doxygen.com. It's a great website, or ask on the forum. In setup, I'm using my servo.attach to servo pin, which is PWM pin 9 in our case. Again, this is essentially pin mode, but for the servo library. I'm setting up communication with the serial monitor at a 9600 baud rate. Because again, that's how I want to. This is not necessary, and it wasn't part of the coding challenge. It's just how I want to be able to switch between what coding challenge I'm doing. I'm outputting just a message saying, "Hey, enter default, reverse, rescale, or light to switch between the modes." And I put them all in lowercase here, but the coding accepts them case insensitive, so it doesn't matter how you type them in, as long as the spelling's correct. In the loop, I'm calling read serial command, which is a function that I'm just going to jump right to it. That is essentially listens for the input via the serial monitor and then adjusts the program's behavior based on the commands received. Again, this is how I'm switching between default mode, reverse mode, scale mode, and light mode. So it's a non-value returning function, doesn't take any parameters. All it does is it's basically encapsulating all this code, which I could have put directly in loop. A common way to check if something's been typed in the serial monitor is to go if serial.available. This returns true if there's something available, and false otherwise. If there is something available, I'm going to read a single character at a time. There's numerous ways you could do this. You could read string until something, like until the next line. That's a common method. So a common method is serial.read string until, and pass in typically the next line character, which is after someone types enter. I started doing it that way, and I kind of ended up switching to this, but numerous different ways to do something. That's the beauty of programming. So in this case, the serial.read method just reads a char at a time, a single character at a time, which I'm assigning to this char variable received char. And then I'm going to increment my command string, which is that string variable I created at the start, which starts off as an empty string, and I'm just going to increment it every time I receive a char. So I'm going to keep reading, as long as there's something available, I'm going to keep reading a character at a time and incrementing this string, so appending the character to my command string. If there's nothing available, as soon as there's nothing available, which will happen once I'm at the end of the line, or the string, I'm done the string, whatever the command they typed in default, after I get through the T, there's going to be nothing available, and then I'm going to come in and I'm going to call the trim function on command, on that string. The trim function just removes any white space if I type white space in front or back or whatever. And then I'm going to try to match the command that the user typed in to the predefined options I've given them. If command dot equals ignores case, this is a function in Arduino associated with the string class, and it just basically checks if the string you typed in is equal to default, and it, like as the name implies, it ignores the case. So you could type in all caps default or some mixture of lower and uppercase, and it will just, as long as, you know, case insensitive, they typed in the word default, this will return true. And I do that for reverse, rescale, and light. And if this is true, meaning if they type default, I'm going to call this method called setMode, which is a function I created, and I'm going to pass in 0. If they typed in reverse, I'm going to call the setMode function passing in 1. I'm going to pass in 2 to the setMode function for rescale, and 3 for light. Finally, if they typed an empty string, meaning they didn't type anything, so if they didn't type anything, but they just pressed enter or something, I'm just going to put current mode in the set mode function, and current mode will be whatever they're currently on. So 0 for default, 2 if they were on rescale. It's just going to be whatever they were already on. It's essentially just going to not do anything. Else, if they've typed anything else weird, like they've typed in cheese, I'm just going to put invalid command and ask them again to enter one of the valid commands: default, reserve, rescale, or light. And then at the end, I just clear the command buffer by setting the command string back to an empty string. Here's the set mode function. I know I'm kind of a little older. I'm just showing you the functions I've created first. But again, this function checks if the requested mode is different from the current mode. And the reason I did this is because, again, if they're already on default mode and they type default mode in again, I don't want it to show up over and over and over and over again on the serial monitor if they're already in that mode. I only want it to show up if they were in default mode and then they switch to reverse mode, or if they're in reverse mode and switch to, you know, light mode. I don't want them to be in light mode and then keep typing in light mode, and I don't want to keep printing it to the serial monitor. So this is really just preventing that from happening. So again, if the mode changes, it updates the current mode and sets the mode change flag, that Boolean flag I had at the start, to true, allowing a new mode message to be printed. So basically, set mode, it took in a mode. Remember, I was passing 0, 1, 2, or 3 in there, or current mode. I take that mode in, and then if the mode is different than the current mode, meaning it is a different mode, they typed in a different command than the mode they're currently on, then I'll update current mode to whatever they typed in, to mode, and I'm going to set my mode change Boolean flag to true. And then I'm going to come down here, if mode change, which if I just went through this, it is true. If mode changed, and again, I don't have to put equals equals true. I could, if I wanted to be really explicit, I could go equals equals true, but that's not necessary. This is a Boolean anyway, so if it's true, this will return true, and if it's false, it will return false. So if the mode changed is true, meaning they were on one mode and then they typed in a mode that was different than the one they're on, then I'm going to print a mode message, which I'll go to that code in a second, another user-defined function I've created. And then I'm going to reset the Boolean flag to false. The print mode message, again, this function just uses a switch statement to display a unique message for each mode. It is called only when the mode changes to avoid redundant outputs. Again, I don't want a bunch of outputs on the serial monitor. I only want it to show when they've changed. So again, I just use a switch statement. I take in the current mode, whatever that was. I don't take it in, rather. The current mode is a global variable. And if it's 0, that means they're in default mode. I just print that to the screen. 1, they're in reverse mode. 2, they're in rescale mode. And 3, they're in light mode. And then if there's nothing else that's going to be able to come in here, but, you know, by convention, you often put a default in a switch statement as a catch-all. So in this case, I'll say I'm in default mode because I'm not going to get to that anyway, but I'd be in default mode. Okay, so that was the tangent with read serial and all those functions. So I'm going to go back to the loop where that first happened. So again, we call the read serial command, which basically gets that command from the user. The user types something in and we check that command. I'm going to be constantly reading every loop. I'm going to do an analog read on the potentiometer pin and assign that to pot value. Then I have my servo position variable, which is set to 0 by default, but that's going to change based on the pot pin. And I'm using this switch statement to pass in the current mode, whatever that is, based on what the user typed in, and I think I started off at 0, so it starts off in default mode. I jump in here and I do something based on the mode I'm in. So if I'm in 0, which is the default mode, the servo position is just going to be using the regular mapping that we used in the previous circuit, where we map the pot position, which is normally 0 to 1023 range. We just map it to servo min and servo max, which are my variables representing 20 and 160. So that's the same as the last circuit. And I originally was printing something off, and then I switched. I took these print statements out. That's why they're commented out, because I used my print message function to take care of that. If we're in case 1, I mean if current mode is 1, that means we're in reverse mode. And then I call the map function, but I map what should be the minimum, the 0 value, to servo max, and I map what should be the maximum value of potentiometer to servo min. So I just switched these values around. If I'm in rescale mode, I'm mapping the 0 to rescale min, which if you remember is like 80. Let's go back up there. It's 80, and rescale max is 110. So I'm still doing mapping, and it's the regular mapping. It's not reverse mapping. It's regular mapping, but the values are now going to be between 80 and 110, a lot smaller. For case 3, light mode, now I'm going to do an analog read on the light pin, which we know is pin A3, and I'm going to assign that to light value. And now my servo position is not going to be based on a mapping of pot value. It's going to be based on my photoresistor value, the voltage circuit, divider circuit I've created. And I'm still going to get a reading from that of 0 to 1023. I might actually not get quite that, depending on the thresholds of the photoresistor. I didn't really check that, but you would check that to get, to make sure, but it still works fine. And then I'm just mapping that between the regular servo min and max, so between 20 and 160. And that's it. And then the default value, again, we're not going to get the default value, but by convention, it's good coding. Just always have a default with your switch statement. I'm just going to go back to the regular mapping. And that's pretty much, and then after that, so I'm still in this case statement. I'm still in this switch case, I'm out of the case statement. I'm still in the loop. I'm going to go if mode change, and that's that Boolean variable, right? That I only want true if I'm in a mode and I switch to another mode. I don't want that just happening anyway. But if the mode has changed, I'm going to call the print mode messages. So that's where I go down and I print what mode I'm in, only upon a change. And then finally, I'm going to go, I'm going to set the mode changed Boolean variable to false again. So again, my flag is true, and then I come in here and print the message, and then I reset my flag back to false. And then I'm going to show a quick demo. I'm going to show a quick demo.